Hey there, welcome to my YouTube channel. In this video, we are going to talk about orthogonal diagonalization. Let's quickly have a recap of what we did in the earlier video. In the earlier video, we talked about orthogonal matrices. We saw the definition of what an orthogonal matrix is, a couple of examples, and also some important properties which are going to help us in orthogonal diagonalization. So in this video, I am going to state what do we understand by orthogonal diagonalization, and we will also see a simple example to understand the concept. Let's get started. A matrix A is orthogonally diagonalizable if there exists an orthogonal matrix Q such that Q inverse A times Q is going to be D, where D is the diagonal matrix whose diagonal entries are the eigenvalues of A. Now, also in the earlier video, we had seen that if a matrix is orthogonal, then its inverse is nothing but its transpose. So we can rewrite this expression as Q transpose A Q should be equal to D. Let us see a quick example. So here we have a 2 by 2 matrix A whose entries are 5, -2 and -2, 2. We wish to check whether the given matrix is orthogonally diagonalizable. We will be starting with finding the eigenvalues, its eigenvectors, check the eigenvectors if they are orthogonal, and finally have a conclusion. To find the eigenvalues, we are going to use the shortcut method of finding the characteristic equation that is given by x square minus trace of A plus determinant of A is equal to 0. Applying it over here, we will be getting lambda square. The trace of A is 7, so minus 7 lambda, plus the determinant in this case is 6 is equal to 0. It's a quadratic equation and its linear factors are lambda minus 1 and lambda minus 6 equal to 0. So thus we can see that the two eigenvalues are lambda 1 equal to 1 and lambda 2 equal to 6. And very evidently these two eigenvalues are distinct, so we can say that the matrix A is diagonalizable, of course. Now for the next part, we are going to find out the eigenvectors corresponding to these two eigenvalues, and for that we will be starting with the equation A minus lambda I times x is equal to 0, where x is the eigenvector and 0 is the column vector 0. So for lambda 1 equal to 1, it reduces to A minus I times x is equal to 0. So A minus I is going to be 4, -2, -2, 1, and x is xy is equal to 0, 0. It can be seen that the first row is twice that of the second row. That means it is linear combination of the second row. So we could reduce this matrix equation to a single system of linear equation, -2x plus y equal to 0, which gives us that y is equal to 2x. And if we keep the value of x as 1, we get x as 1 and y to be 2. This is the eigenvector corresponding to lambda 1 equal to 1. And for the second eigenvalue lambda 2 equal to 6, we will be beginning with the matrix equation A minus 6 times of I times x is equal to 0. And A minus 6i is going to be -1, -2, -2 and -4. xy is equal to 0, 0. Again, the second row is 2 times of the first row. That means it's a linear combination. This particular matrix system will reduce to the equation -x, -2y is equal to 0, and which gives us that x is equal to -2y. So if we plug in the value of y as 1, we will get x as -2. So thus x2 equal to -2, 1 is the eigenvector corresponding to lambda equal to 6. Now we wish to check whether these vectors are orthogonal. And for that we will be considering the inner product of the two vectors. So inner product of x1 with x2. In this case, we'll be considering the inner product to be the standard Euclidean inner product, also known as the dot product. So this is going to be 1, 2 with -2, 1, and that's 1, 2 dot -2, 1. So in this case, it is -2 plus 2, which is 0. So thus, inner product of x1 with x2 is 0, and this implies that the two vectors are orthogonal to each other. And since the eigenvectors are orthogonal, we could eventually end up saying that the matrix A is orthogonally diagonalizable. Now the last part is to find out the matrix Q for the expression Q transpose AQ equal to D. And this matrix Q is given by the normalized eigenvectors. So by that we mean we will be finding out x1 hat, which is given by x1 divided by norm of x1, and that is going to be the vector x1, which is 1 2 divided by its norm, which is square root of 1 square plus 2 square, and we get x1 hat to be 1 over root 5 and 2 over root 5. Likewise, x2 hat is given as the vector x2 divided by its norm, and this is going to be negative 2 1 divided by square root of negative 2 square plus 1 square, and that gives us negative 2 over root 5 comma 1 over root 5. So the matrix Q is given by, so the first column will be x1 hat, so that's 1 over root 5, 2 over root 5, and the second column will be negative 2 over root 5 and 1 over root 5. By the nature of construction of this matrix, we already are aware that Q is going to be orthogonal. So thus, applying the result, the transpose of Q is going to be the inverse of Q, and this is going to be 1 over root 5, negative 2 over root 5, 2 over root 5, and 1 over root 5. So thus we have found out Q and Q inverse. Now all you got to do is you got to calculate the product of Q inverse AQ and check that whether you get it to be the diagonal matrix 1 0 0 6. And if yes, then you have done your calculations correctly and you could conclude saying that A is orthogonally diagonalizable. And if not, then you should reconsider checking your calculations and get it done one more time and correctly. If you like this video, then do hit the like button and share it with your friends who are also studying linear algebra and help them out. Also subscribe to my channel and hit the bell icon to keep yourself updated about the upcoming videos. Thank you so much for watching till here and happy learning.